So we're on to question 7, the first of the problem-solving questions. And it's a typical leaving cert type question in that we start off a little story. A scientist is studying the population of fish in a lake. The number of fish in the population after T years of the study is modeled by the equation. Okay, so you got a bit of language there to read through, but we can see very clearly what it's about. N is the population size. T is our kind of independent variable, and it's in terms of years. So it's not too bad to get a kind of sense of the question. Find, according to the model, the number of fish in the lake at the start of the study. So with this one, it's the same kind of trick that comes up a lot with this. You just have to recognize that the start of the study, T is equal to 0. Okay, that's fair enough. Sometimes people put in 1 by mistake as the start, and that'll throw it off completely. Because if you have here e to the power of 0.2 times 0, 0.2 times 0 is 0, and e to the power of 0 is 1. So therefore, you're going to end up with 250 over 1.25, you're going to end up with 200. Okay, so once you know that T equals 0, it's a grand easy 5 marker. Find, according to the model, the value of T when there are 800 fish in the lake. So 800 fish in the lake. So in that case, that's my output. That's my N. Find your answer correct to the nearest integer. So I just have to remember that part for the end. So my output here is 800. Well, how do you solve any equation? You isolate the variable. So that's what I'm going to do. I multiply across by the 1 plus 0.25 times e to the power 0.2t. What happens next? I multiply the 800 through the bracket. And by doing so, I end up with 800 plus 200 times e to the power 0.2t. I'm going to subtract this guy away from both sides, minus 200. E to the power 0.2t from both sides. And I end up with 50 times e to the power 0.2t is equal to 800. I can divide across by the 50, get e to the power 0.2t is equal to 16. My variable is in the power, so I can use logs. Okay, so I'm going to do it in 2 different ways. I like to use what I call the key rule of logs as much as I can. And what that is this. If a to the power of b is equal to c, that implies the log of c to the base a equals b. And the implication actually works in both ways. Either way, you could start with the logs and go to the indices, or the other way around. And with this, what I always say is, when going from indices to logs, the base remains the base. The other 2 switch place. So for me, with this question, what I could be doing is the following. I could say, right, I'm here at this point. I introduce logs. The base remains the base. What was the answer becomes the power. What was the power becomes the answer. And then I just divide across by the 0.2. And I put all that into the calculator and I get my answer. So I could do it that way, right? And of course, that is ln of 16. And that's the way I generally like to do it. But I know possibly the majority of people still would do it this way, where they would take ln, the natural log of both sides. And what you have then is like ln is log to the base e. So you have e to the power 0.2t, the log of e to the power 0.2t to the base e. When you have one power raised to another power, you can bring the power to the front. Okay, so the power to the front law. So then I'd have ln of e, or log e to the base e, which is 1. And so I'd have 0.2t times 1. So I just have 0.2t is equal to ln of 16. And divide across by the 0.2, and I get the answer. And of course, I need this correct to the nearest integer, so it's 14 years. And I always say to students, you've done all the hard work. You don't want to give away a couple of marks here at the end by not having the 14 years. You want to make sure you get those marks. So you just read the question through again at the very end. Okay. Use calculus differentiation to show that dn dt is equal to, we see what it's equal to here. So what am I going to do? Well, I can see my function, and obviously it's a quotient, it's a fraction. So I'm going to call the top u, I'm going to call the bottom v. You know, it looks a little bit tricky. We remember, of course, that, you know, if y is equal to e to the power of x, then dy dx will be equal to e to the power of x. It won't change. If y is equal to e to the power of ax, dy dx will be equal to a times e to the power of ax using a chain rule. Okay, so I got to remember that second one, because when I start differentiating here, I'm going to have my du dx is the derivative of the top. So it's going to be my 250 times e to the power of 0.2t, but multiplied by, in the general formula, was a. Here the a is 0.2. The dv dx, same idea. Okay, so in this case, the dv, here's v, right? So when I'm differentiating it, again, I got to be just careful that the 1 is going to disappear, but then I'm going to have 0.25 e to the power 0.2x, or t, I should say. But again, it's times the 0.2, the coefficient on the t. So I can tidy those up a little bit. Okay, I can tidy those up a little bit. 250 times 0.2 will be 50. And 0.25 times 0.2 would be 0.05. Okay, that's that guy there. So what are we doing here? Quotient rule. It's v times du dx plus u, or minus u times dv dx all over v squared. So what is that? It is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom to be squared. So I have it here. You know, there's a bit of work in this now to tidy it up. In the way I described it, that this guy would probably be to the right of this other bracket here, but either way, it's equivalent. So I'm going to be multiplying through those brackets. You know, you'd remember that if you had like e to the power of x times e to the power of y, you'd have e to the power of x plus y. You know, when you're multiplying the same base, you'll be adding the powers. So just got to be careful with that here when I'm multiplying through. So, you know, 50 e to the power 0.2t times 1 will give me the 50e times 0.2t. You know, there's no change. But then when I multiply 50 times the 0.25, that's going to give me 12.5. E to the power 0.2t times e to the power 0.2t. Again, you're adding the power, so you're going to get e to the power 0.4t. Again, 250 times e to the power 0.2t times 0.05 e to the power 0.2t. Well, what's going to happen here? Now, finally, it's kind of starting to come together. I have a minus 12.5 times e to the power 0.4t, again, adding the powers. But thankfully, we can see this guy's going to cancel down these two. So all of a sudden, it starts to look a bit easier. Now, just as a reminder, what's underneath the line? Underneath the line is the original denominator squared. So now that is my answer, isn't it? That's it, because I was just asked to show it. And it was 10 marks. Now, find, given that dn dt is equal to 10, or like when dn dt is equal to 10, so what is that? That's the rate of change of the population with respect to time is 10. Find the value of t to 1 decimal place. And again, like, this might look a bit tricky, but remember, you could have done this part D without doing part C, because we know this bit here, we're given this bit. I multiply across by my denominator at this point. I'm going to have to square out the bracket. So, you know, you just remember, if you have x plus y squared, you square the first, you square the last, you multiply the first times the last and double it. So same idea here. You know, when I'm squaring out this bracket, what's going to happen? I'm going to square the first. So I get 1. I'm going to square the last. So I'm going to get 0.25 times 0.25, 0.0625. or e to the power 0.2t times e to the power 0.2t is going to give me the e to the power 0.4t, as we've seen earlier on. If I multiply 1 times 0.25, I get 0.25. I double that, I get 0.5. And it'll be 0.5 times e to the power 0.2t. Okay. So I'm going to multiply through the bracket by 10. Okay, I'm looking over here on my left-hand side. That's 50 e to the power 0.25. And I got a 5 e to the power 0.25. So when I start to tidy this up, I get as far as here. Now, I can divide everything by this coefficient to make it a little bit easier for myself. Divide everything by 0.625. So now I have e to the power of 0.4t as my upper power, let's call it that. I'm minus 72 times e to the power 0.2t and plus 16 equals 0. Obviously, it is looking like the form of a quadratic equation. So in my next part here, my next move, I'm going to let y equal e to the power of 2t, 0.2t. Why is that? Well, if I say y equals e to the power of 0.2t, well, if I say what's y squared, that's going to be equal to e to the power of 0.2t to be squared. In indices, remember one power raised to another power, we multiply those powers together. So I get e to the power 0.4 t. So when I'm multiplying those powers together, I get e to the power 0.4 t. That's exactly what I have here, e to the power 0.4 t. So what have I got? That means that this guy here is y squared minus 72y plus 16. Into my minus b formula, I'm going to get two answers here for y. I'm going to get y equals 36 plus 16 root 5, or y is equal to 36 minus 16 root 5. Am I finished? No, I'm not. Why? Because I had to solve the equation in terms of t. T is the variable that I'm looking for, not y. So I go back to here. E to the power 0.2t is equal to 36 plus or minus 16 root 5. So again, if I just took the plus case first, I might use, in this case, the key rule of logs. I'd introduce logs. The base remains the base. What was the answer becomes the power. And what was the power becomes the answer. And then I divide both sides here by the 0.2. So I get log 36 plus 16 root 5 to the base e. And of course, I could just call that ln is equal over 0.2 is equal to t. I'd put that into the calculator and get my answer. Or I can do it this way, where I'm going to say, I'm going to take ln of both sides. Ln is log to the base e. Again, same idea. One power raised to another power. I can use the power to the front law. Ln of e is 1. So I get 0.2t is equal to the ln of 36 plus or minus. So there's two cases going on here. I can divide across by the 2. And I'm going to put into the calculator separately the plus case and the minus case. I'm going to get two answers. T is equal to minus 0.7, or t is equal to minus 7.5. That's not going to happen because it's not going to be a negative time. So I get 21.367. Correct in one decimal place, it is 21.4 years. So that was a long part of the question for 15 marks. And what does it mean again? It means after 21.4 years, the rate of change of the number of fish in the lake is 10 fish per year. So that's what that question means after all that work. So look, that was a tough part. And what I think we'll find is probably a lot of students will have started off with this question. They say, oh, I know how to start this one. Great. I'll start this. And then they'll have got to this part and they'll have struggled. However, you still picked up your low partial credit, your mid partial credit in that question. Okay. Last but not least, by graphing this function between 0 less than or equal to t less than or equal to 70, deduce the maximum number of fish the scientists found the lake could sustain. So when you put in these values, and you can use, you could do mode 3 on your Casio, mode 2 on your new Sharp if you have it, and say start 0, steps 5, end 70, something like that, or even steps of 10, and you're going to get a graph that looks like this. course, we have our first value from way back at the very start of the question. So when t is equal to 0, n is equal to 200. And we can see at t equals 70, we're up here to 999.99. So the limit of that function, which is the maximum number of fish the lake can sustain, is going to be 1,000 fish. So it's 1,000. And that was a 10-mark question. So what I'd say, after all the hard work of the previous part, this last part here for 10 marks was actually a relatively straightforward question. So what would I say again? Just, I suppose the moral of it is just to keep hanging on in there, working through the question, and don't give up on it. Of course, a lot of people have got stuck in part D. You mightn't have finished it out properly, but you know what? You'll still probably have picked up a good few marks in it.